Here we are again with a new video lesson. I will be your host, Mrs. Byrie, on the exciting journey of describing quantitative data with numbers. Describing quantitative data with numbers, and after this section you should be able to measure the center with the mean and median, measure the spread with standard deviation and interquartile range. I will let you know that standard deviation is on video 1.3b, which you will watch next week. You will also be able to identify outliers, construct a box plot using a 5-number summary, and calculate numerical summaries with technology. All right, I'm back. Took a little side trip, just picked up some Chipotle. I'm going to eat that in a few minutes because I'm stuck here forever. I just thought I'd throw that in case you were hungry for Chipotle, and then you might want to stop what you're doing, go get some Chipotle, and then eat it while you watch the rest of this lecture. I just try to make it fun, people. All right, back to measures of the center. So let's talk about the mean. The mean is the most common measure of center, and you already know what it is. It's the average. To find the mean, and now this is where we start having some new symbols, that we use in statistic, and you're going to have to really know what the symbols are and what they mean. Okay, so the mean has a symbol, and the symbol is X bar, and it is an X and a bar. I know, shocking. All right, so we call the mean, or X bar, a set of observations. We add their values and divide by the number of observations. Now, in a long form, it looks like this. X bar equals x1 plus x2 plus x3 plus ... xn. N meaning just the last number that you've got, divided by n. Now, we also have a shorter form that we can write this as, and that is using a special new symbol called sigma. And so this is X bar equals sigma xi, meaning your total number, the sum of all of them, divided by n. You will see it more frequently in this type of written than in this type up here, just because this is shorter and more compact. This symbol right here, only means to sum. It's just a summation symbol, and most of you guys already know that. All right, so here is a guided example. Here's some data on travel times to work from a sample of 15 North Carolinians. It's already in a nice, handy-dandy stem and leaf plot, and we're going to do two things. Over here, we're going to first calculate the mean travel time for all the 15 workers, and then we're going to calculate the mean again, but we're going to take out the person who went 60, because 60 kind of doesn't seem to fit. That might technically be an outlier. We're not sure yet. All right, so we're going to add them all up. Wow, that's a lot of adding, but basically, X bar is equal to 5 plus 10 plus 10 plus 10 plus 10 plus 12 plus 15 plus 20 plus 20 plus 25 plus 30 plus 30 plus 40 plus 40, and this time we're going to do it plus 60 all over the total number that we have. In this case happens to be 15. Well, if we do that, what we end up with is 300, no, wait, let me see. It would probably help if I get a calculator. Hold on, I'll be right back. All right, so this equals 337 divided by 15, which is about 22.5 minutes as the average or mean commute. Now, the second part said that they want us to do this without putting in that 60-minute interval. So I want to know what happens if I take out the 60 minutes, and so this would be, I'm going to just label this X bar O, meaning I've got rid of the outliers, and I've got 220, sorry, not 227, but 277. 277 divided by 15, which is 19.8 minutes. Now look, not mutes, minutes. Now I want you to notice, though, the important thing is that you see that that one score, that one 60-minute score, really affected the commute time that we see here. With the 60 minutes, you're looking at 22.5, but that's really not a great average. It's really closer to 19.8. So we talk often about the mean not being a resistant measure. Resistant meaning that it can be affected by outliers. And means are easily affected by outliers. So we often don't use them. One measure that is that is more resistant to outliers is the median. And we represent the median by the capital M that's usually italicized. I know it's kind of boring, but that's just what the median gets. It's kind of sad. I'm sure it's just very sad. All right, the median M is the midpoint of a distribution. It's the number such that half the observations are smaller and the other half are larger. So there's 3 steps to finding the median. First, arrange all the observations in order of size. Arrange observations or data in order of size, and this is where you really want to use your calculators to do this for you and not waste time. And we want to go from smallest to largest. Next, if the number of observations is odd, it makes it easy. Then M, or the median, is the center observation in the ordered list. Now, that just means that if you have 13 different numbers, the median is the 7th number once you put them in order. Now, if n is even, the number of observations is even, then the median is the average of the 2 centered observations. And we'll do an example like this. You guys have been doing this for a while. I don't think it's going to be that difficult. All right. So here's a perfect example we've got when n is odd. All right, when n is odd, and this is the same bit of information we were using before, but notice we've put things in order from least to greatest. Now, since this is odd, we're going to count the number of points that we have, and you can, I think it's 15, but we'll do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. All right, so 15 is odd, so we want to do the middle number, which is going to be 8. You're going to have 7 points below and 7 points above. 1, 2, 3, 4, 5, 6, 7. That should be my center number, and I should have 7 numbers above. I do. So the median is 20. Now in this case, I have n is even. And I've also made a mess of this because what did I do? I did not put this in order because I mean that way. So what you want to do is go ahead and put this into your calculator, into a list so that it will do it for you, or you can just do it yourself. It doesn't really matter. This one's not too big, so I know I'm going to do 5, and when I do these, I usually cross off the numbers as I use them. 10 and 10, right? And then it looks to me like I've got some 15s. 1, 2, 3, 4. And then I've got some 20s. 1, 2, 3. And what am I up to next? 25, a 30, a 40. Get rid of those guys. Oh, look at that. I did that too early. All right, I got 2 30s and then a 40. And then I have 2 60s, 60, 65, and 85. Wow, that is a range of data. All right, so this is even, so I should have an even number on each side. So you'll notice I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I've got 18 different data points. So I know that the split would be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. Now, this one works out nicely because I have 9. There's 9 below. There's 9 data points above. So I know that the point in between these two numbers would be, the average of that would be my number. Well, this one works out well because they're both 20. So guess what the answer is? 20! But if those two numbers were different, you take the two numbers, add them together, and divide by 2. All right, so there's some important symbols that I wanted us to go through. Let me find my notes really quickly. First of all, just to remember that this means X bar or mean/average. This capital M means median. X to the I just means all the values in the data set. N, it's always a little italicized N, means the number of observations or number of values. And then we have sigma, which is a sum, or as I like to say, add them up. Now, I do want you to notice right here, I do have one thing. This X bar here, this is for a sample statistic, and we'll get into this more later. This is sample mean. This is sample mean, which is the X bar is what we use when we're just talking about a sample. If I were to use a population mean, I actually have a different symbol for that, which we will get to in later chapters, but just so you know it, the population mean is represented by this symbol right here, which is mu. Not to be confused with mu. But we'll deal a lot with that later on. So, fun times ahead. All right, so what does mean mean? What does it mean? Right now in your head, what does the word mean actually mean? Well, Mrs. Barry, I don't know. What does mean mean? Well, basically in common language, mean means the fair share value. It means the fair share value. If I was going to divide all of the values up and put them equally amongst every single person in the group or individual in the study, this is their fair share. It's the amount that everyone should get. So basically, you're splitting all the values equally among all the individuals. All right, so we can compare the mean and the median together. There's just basically a couple of things you want to know. If the distribution is symmetric, not symmetry. but symmetric, then the mean and the median will be close together. Or even exactly the same. But if your distribution is skewed, the mean will be farther out on the tail. Than the median. So if I had a distribution that looked, I'm just drawing these quickly, if I had something like this, then your mean would be somewhere down here, and your median would be somewhere in the middle. But if it was skewed right, it would just be the opposite. You would have a mean up here, and the median would be lower. That question will come up because they're going to want you to be able to evaluate the difference between the mean and the median. So this is an important little fact that you need to know. Okay, so here's a quick check. We're going to look at the STEM plot of travel times to work for New Yorkers, 20 randomly selected New Yorkers. And we already know the median is 22.5 minutes. And what we're going to do is just answer these questions. So we've got a stem and leaf plot that's already built for us. Hallelujah. We don't have to do it ourselves. We always like that. And we want to know what the answers to these questions. So based on the stem plot, would we expect the mean travel time to be less than, about the same, or larger than the median, and why? Well, because the distribution is skewed to the right. Now, I know you're like, Mrs. Bari, this is up and down, it's not skewed. Well, flip it sideways, and you would see that it would be skewed to the right. We would expect the mean to be larger. Because of the right skewed. Because the distribution is skewed. Okay, so then it wants us to find the mean travel time, and I would suggest that you plug this into your calculator right now, and I'm going to give you a few seconds to do that. Time's up. Were you able to do it? I suggest you pause this thing so that you can find out the answer yourself. All right, but if we did the mean and we added everything up, we would find that the mean of this is 31.25 minutes. Now notice the median is 22.5. So let's interpret this. And is it, was the answer to question 1? Well, yeah, it is greater. Look at that, I just proved it. Now we want to interpret the result from question 2 in context without using the word mean or average. So how about this? If we divide up the travel time evenly, among 20 people, each would have a 31.25 minute drive. There we go. We just interpreted it without using average or mean. Now, which one do you think would be a better summary of center? Well, because this is skewed, and this often happens, if you have a skewed situation, that means you might possibly have outliers. And the data is not well distributed around the center. So I would say, in this case, the median would be a better summary of center because it is a skewed distribution. right, next topic, measuring spread. Now we're going to use the interquartile range, or IQR. Some of you have already learned this. I hope so. So this should be pretty quick and easy. So a useful numerical description of a distribution requires both a measure of center and a measure of spread. We want to know all about the center and the spread. And this, we're going to learn one thing today on the interquartile range. That's going to be a measure of spread. And then our next lesson that we do is the second half of this video, which we'll learn about another measure of spread called the standard deviation. Whoop, whoop, so much fun, lots of math. All right, the simplest measure of spread is the range, right? Or, sorry, the simplest measure of spread, or what we also call variation. Remember that word, and we'll come back. All right, so the simplest measure of spread or variation is, we already know it. What is it? The range. Oh, thank you, class. You're so good at answering me when there's no one else in here. You know the Facebook quiz that asks you how crazy you, that figures out how crazy you are? I'm like 93% crazy. It's because I talk to myself. But that's working out really well when I make these videos because I'm just talking to myself anyway. So, yeah, I might be crazy, but that's okay. Hopefully it'll be more entertaining for you. All right. Now, what is the possible problem you could have only by using the range? What possible problem could we have if we only use the range to describe the spread? I really hope, students, that your little brains are just doing a little happy dance when you remember the word, there's a possible outlier. Is there a data piece that doesn't fit? Well, if there happens to be an outlier, that can mess up our range. It can really throw things off. So we have a better way to measure this, and that's with the interquartile range. All right, the interquartile range, or IQR, measures the range of the middle 50% of the data. We call this, wow, what was I going to put there? Hold on. Okay, it took a little bit, but it came to me. We call this a resistant measure of spread because it ignores the smallest and the largest values in a distribution. The smallest and the largest, I don't know what word I was going to put there, but we'll just go with values, the extreme values. So what we're going to do is we're going to find the IQR. And here's basically how we do it. We'll do it on the next page. We find the mean. That is completely wrong. Look at that. I put that in there to throw you. We don't find the mean. We find the median. So cross that out. Then we find the first quartile. We label this Q1. We find the third quartile, Q3. And we find the IQR, which is Q3 minus Q1. Mrs. Byrie, I don't know what these Q's are. What are you talking about? Do you know what she's talking about? I don't know what she's talking about. Okay, let's find out. All right, children, I'm going to answer your questions on the next page. All right, so we're going to do another example. So we've got our North Carolina traffic here, again, and we're using our 15 workers' travel time, and we've arranged them in increasing order. So we have a set that looks like, well, it should not have this here. Somehow we have a mess there. Okay, we should have, let me find my data. Things are crazy, crazy, crazy. We should have 4 10s. Okay, we're good. All right, so I'm going to count here. We should have 15 workers. So if it's 15 workers, we are looking for the 8th number. 1, 2, 3, 4, 5, 6, 7, 8. So we are looking at this number right here. This number is the median. Now, we want to look for the upper quartile and the lower quartile. The lower quartile we call quartile 1. And we find quartile 1 by looking at this set of data. And basically all we're going to do is find the median of this set of data. So we have 7 pieces of data here, so we know that number 4 is our median of this data. So 1, 2, 3, 4. So that is quartile 1. Likewise, we're going to do the upper quartile with the top 7. So the 4th term is my median of that set of data. So I've got quartile 3. Now remember, the IQR is quartile 3 minus quartile 1. So in this case, it's 30 minus 10, which is 20. So our IQR is 20. That is the measure of spread that we have. That's all there is to it. Now, the quartile 1, quartile 3, those are important, and we're going to use them in just a minute to do a box plot. All right, one more time. Here's a stem plot of travel times to work for 20 randomly selected New Yorkers. So we've got 20. It's an even number. So I know that my median is going to be in between 10, number 10, the 10th one, and the 11th term. All right, so I'm going to find my median. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this one is 10. It's a 0. Now 11 is a 5. So I have to figure out the average. So my median is 0 plus 5. That's the 10th plus the 11th divided by 2, which is 2.5. So we add that with our 2, and we get 22.5 being our median. So our median is 22.5. Now, we got to find our quartiles. So since this is halfway in between here, we are going to include that 0 in our lower bit of data. So we know that there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces of data. We're going to have to do this median thing again. So we're going to start here, and we're going to count, and we know it's between 5 and 6. 1, 2, 3, 4, 5, and 6. Well, 5 and 6, nicely done. It's just a 5. So quartile 1 is 5. Here's our upper set of data, including the 5, all the way to this 5. So 1, 2, 3, 4, 5, 6, in between 5 and 6. So again, this is going to be 40 plus 45 divided by 2, which is 42.5. So quartile 3 is 42.5. All right, great. So now we're going to do the IQR. Did I say that was 5? That's actually 15. I wasn't paying attention. All right, so let's do the IQR. The IQR is quartile 3 minus quartile 1, which is 42.5 minus 15, which happens to be 27.5 minutes. All right, that's it. So how do we interpret this? The range of the middle half of travel times. Remember, this is just the middle half. For New Yorkers is in the sample and when writing these in your homework, you can write them exactly the same, only just change the numbers and things. 27.5 minutes. There you go. All right, key vocabulary, outlier. I told you earlier an outlier is something that doesn't fit, but I did not give you a specific thing to do. Well, the outlier actually has a rule. There's several rules. This is the most common rule. We're going to use this one. And it is the 1.5 times IQR rule. And literally all it means is something, a value is an outlier if it falls more than 1.5 times the IQR above quartile 3 or below quartile 1. Now notice, a little bonus diary for you people. Yes, I have my own hashtag just in case you wanted to know. Lexi did it. It's kind of fun. I feel special. On the AP exam, you may be asked to identify outliers and tell the rule you used. You have to tell them the name, the 1.5 times IQR rule. I know it sounds dumb, but trust me on this, little bonus Byrie knowledge might help you in the long run. All right, so does the definition of outlier identify any outliers for the New York travel time data? Well, 1.5 times our IQR, which is 27.5 minutes, equals, let me use my handy dandy calculator, 27.5 times 1.5 is 41.25. Wow, that's a lot. And we're going to add that to quartile 1, or subtract it from quartile 1. So that would be a negative number, so there's no lower outliers. And we would add this to quartile 3, which would be 83.75. So an outlier above quartile 3 would have to be greater than, what did I just say, 83.75. And we didn't have any of those, so we did not have any technical outliers. Things may not look like they belong, but unless they fit the 1.5 times IQR rule, they are fine. All right, determine whether the McDonald's Premium Crispy Chicken Club Sandwich with 28 grams of fat is an outlier. Okay, that's a lot of fat. Here are the 14 amounts of fat from all sandwiches in order. Okay, first thing we got to do, we got to find the mean. 1, 2, 3, there's 14, so it's in between 7 and 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's in between these two, so guess what? The mean is 16. Our lower quartile is going to use all of this data. So it's going to be in between 4 and 5. So, sorry, 1, 2, 3, 4, 5, 6, 7. Oh, never mind. It's going to be right here. It's 10. Quartile 1 is 10. And then we're going to use all of this data up here. It's going to be 17. So quartile 3 is 17. So the IQR, in this case, is 17 minus 10, which is 7. So outliers would occur if you take 1.5 times 7. 1.5 times 7, handy dandy calculator, is 10.5. And we're going to take 10.5 below quartile 1. So quartile 1 equals 10 minus 10.5 is negative 0.5. So we know there's no lower outliers. Quartile 3 is above quartile 3. So 17 plus 10.5 is 27.5. So because 28 is greater than 27.5, 28 is an outlier. And we do not include it in our data when we are figuring out means and medians. All right, so we're going to talk about a 5-number summary. A 5-number summary is really nice. It's just the 5-number summary. I'm doing quickly because I need to eat dinner. Of a distribution consists of the quartile, the smallest, observation, the first quartile. Get it? Quartiles, quarters, 25% of the data. The median, the largest, the third quartile. Ugh, what am I doing? I'm just really getting tired. The third quartile and the largest observation. Written in order from smallest to greatest. So it looks something like this in shorthand. The minimum, quartile 1, median, quartile 3, and the max. You should have seen these before. We use them to make box plots. All right, so how to make a box plot. A central box is drawn from the first quartile to the third quartile. A line in the box marks the median. Lines called whiskers extend from the box out to the smallest and largest observations that are not outliers. Okay, it's a bunch of words. Let's just do one. It's a lot easier. And I will show you Mrs. Byerly's quick, down and dirty box plot experience. All right, we do not include outliers. So first of all, just know that this outlier, most of the time we'll use a little asterisk to show it, because it doesn't really count. All right, we're going to start with my median. I know that I'm going somewhere between, my lowest number is 9, my biggest number is 23. I'm going to start at 5, 10, 15, 20, 25. And then we know we've really got 30 up here. All right, I'm going to start by putting a box at my median. My median is at 16. I mean, not a box, a line. I put a line at my median, it's 16. I put a line at my first quartile, that is 10. I put a line at my third quartile, that is 17. I connect, I make a box out of these. Now, this is 25% of the data. This is 25% of the data. So this is the middle 50%. Notice this is really skewed, and it's skewed left. Now, we have a minimum of 9, so I put a circle to show my minimum of 9, and I attach it. That's my whisker. And a maximum of 23. And if I want to, I can put my little outlier here as an asterisk. That's a box and whisker graph. So basically, the deal is you've got 25% of your data here, 25 here, 25 here, 25 here. And then the outlier, special, like so many of you. All right, here are the numbers of home runs that Hank Aaron hit in each of his 23 seasons. Make a box plot for the data. Well, the first thing we need to do is find our median, our quartile 1, our quartile 3, any outliers, which means we have to know an IQR, and we want to know a min and a max. All right, so I did some work on the calculator just to help us out a little bit because we're kind of in a hurry. I am going to tell you that the minimum number that he hit was, okay, there we go. The minimum was 10. The maximum was 47. Quartile 3 is at 44. Quartile 1 is at 26. And the median is at 34. Now, if you work all this out, the IQR happens to be 44 minus 26. 44 minus 26. 18. So the IQR is 18. And so if we do the boundaries for that, we would do 1.5 times 18. And we're going to subtract that from quartile 1, which equals -1. And then 1.5 times 18 and add that to quartile 3, and that is 71. So we know that there's no outliers here. So now we're just going to make the plot. We know we're going between data of 10 to 47. So I'm going to go with 10, 20, 30, 40, and 50. I'm going to draw my line. And guys, this is obviously, estimated. My median is 34, so that's, let's change colors to blue. 34, it's about right here. Quartile 1 is 26, it's about right here. Quartile 3 is 44, about right here. Make yourself a pretty box. Add your whiskers. 10, not an outlier. 47, not an outlier. Done. There's my box plot. we'll go in class next time to teach you how to do these on the calculator. All right, we're going to do an activity in class about comparing outliers, comparing box plots. Here's a picture of comparing box plots. You'll notice that up here, this is New York data. This is for drivers, and these are the North Carolinian drivers. We have an outlier that we put an asterisk to show, and then we see the whisker ends at the last data value that's not the outlier. The interquartile range is the length of the box. Okay, and then we can kind of see, in general, what we're talking about. So what do we notice? Well, it looks like definitely the New York is right skewed. It's debatable as to whether the North Carolina is right or if it's almost symmetrical. Oh, no, never mind. Erase that thought. The North Carolina is also right skewed, because don't forget to look at your whisker. So even though the center part of the data, the 50% of this data looks symmetrical, this is long, so it is a right skewed distribution. The center, it looks like the travel times are a bit longer in New York than in North Carolina. And the median, the quartile 1, quartile 3, and the max are larger in New York. The spread is also more variable. Look, there's more spread out variable. This is pretty compact. You've got a larger amount of variation here. So the spread is greater in New York. And the outliers, we had one outlier in New York. There's no outliers in North Carolina. And that's how you compare them. So we can get a lot of information when we compare them. We'll be doing an exercise with this in class. Oh, that's my last slide. So this is the end of part Vend. It's the Vend. It's the end of 1.3a lesson. Don't forget, you might have a possible quiz on this topic. Have a great weekend.